Volcanic eruptions have fascinated and terrified humans for centuries. The explosive power and awe-inspiring beauty of these natural phenomena have sparked curiosity about their underlying mechanisms. While volcanoes may appear menacing, they offer an opportunity to delve into the fascinating world of geology, providing insights into the inner workings of our dynamic planet. In this video, we explore the science behind volcanic eruptions, shedding light on the processes that shape our Earth's fiery fury. The structure of a volcano. At the heart of understanding volcanic eruptions lies the structure of a volcano. A typical volcano consists of a volcanic cone, a central vent, a magma chamber, and various channels and fissures that allow the movement of magma from the depths of the Earth to the surface. Deep within the Earth's mantle, the intense heat and pressure cause rocks to melt, forming a molten rock called magma. The role of tectonic plates. Volcanic eruptions are closely linked to the movement of tectonic plates, the large sections of the Earth's crust that float atop the semi-fluid mantle. Most volcanic activity occurs at plate boundaries, where the plates interact. There are three primary types of plate boundaries: divergent, convergent, and transform. These occur where plates move away from each other, creating a gap. Magma rises to fill this void, forming new crust and giving birth to shield volcanoes, characterized by their broad, gently sloping profiles. The Mid-Atlantic Ridge is a prime example of a divergent boundary. Convergent boundaries: here, plates collide, and one plate subducts or sinks beneath another. As the descending plate sinks into the mantle, it releases water and minerals that lower the melting point of the surrounding rocks. The resulting magma is less dense than the surrounding materials, causing it to rise to the surface, resulting in explosive composite or stratovolcanoes. The Pacific Ring of Fire is a region famous for its volcanic activity associated with convergent boundaries. Transform boundaries: these boundaries occur where plates slide past each other horizontally. While they are not known for generating large volcanic eruptions, the intense friction and pressure can result in the formation of fissures and cracks, allowing magma to reach the surface through volcanic vents. Magma is a key player in volcanic eruptions. It forms when solid rock in the Earth's mantle or crust melts due to increased temperature, decreased pressure, or the introduction of volatiles such as water and carbon dioxide. The composition of magma varies, ranging from basaltic, low in silica, to rhyolitic, high in silica. Basaltic magma is typically associated with relatively gentle eruptions, while rhyolitic magma tends to produce explosive eruptions due to its high viscosity. Volcanic eruptions exhibit various styles, each associated with its own set of hazards. The explosiveness of an eruption depends on the magma's composition, temperature, gas content, and the manner in which the magma interacts with the surrounding rocks. Effusive eruptions: these eruptions occur when low viscosity basaltic magma rises to the surface through volcanic vents and fissures. Lava flows steadily, creating shield volcanoes or vast lava plateaus. Although effusive eruptions are generally less hazardous, they can still pose risks to nearby communities. Explosive eruptions. Explosive eruptions are typically associated with highly viscous magma, such as andesitic or rhyolitic. The high gas content and pressure within the magma chamber cause violent eruptions. These eruptions often result in the formation of composite or stratovolcanoes, characterized by their steep slopes and distinct layers of ash, lava, and volcanic debris. During an explosive eruption, the magma is fragmented into tiny particles, creating a volcanic plume that can reach incredible heights. The eruption column carries ash, gases, and pyroclastic materials, which are a mixture of hot rock fragments and gas, high into the atmosphere. These materials can travel vast distances, posing risks to aviation, human health, and the environment. Pyroclastic flows are another hazard associated with explosive eruptions. These fast-moving currents of hot gas, ash, and volcanic debris can reach speeds of hundreds of kilometers per hour, obliterating everything in their path. Pyroclastic flows can devastate entire landscapes and cause significant loss of life. Volcanic gases also play a crucial role in eruptions. Water vapor, carbon dioxide, sulfur dioxide, and other gases are released during volcanic activity. These gases can contribute to atmospheric changes, including the formation of acid rain and the potential for climate effects. Volcanic gases can also have immediate health implications, leading to respiratory problems and other health issues for those exposed to them. The study of volcanic eruptions has advanced significantly in recent decades, thanks to technological advancements and improved monitoring systems. Scientists use a variety of tools to monitor volcanic activity, including seismometers to detect ground vibrations, GPS to measure ground deformation, gas sensors to measure gas emissions, and thermal cameras to monitor temperature changes. By analyzing these data, scientists can better understand the behavior of a volcano and predict eruptions to some extent. However, accurately predicting the exact timing and magnitude of volcanic eruptions remains challenging. Volcanoes are complex systems, and there are still many uncertainties surrounding their behavior. Nevertheless, continuous monitoring and research efforts provide valuable insights into volcanic activity and help mitigate the risks associated with eruptions. The science of volcanic eruptions reveals the dynamic and intricate processes occurring within our planet. From the movement of tectonic plates to the formation of magma and the release of gases, volcanic eruptions are the result of complex interactions beneath the Earth's surface. By studying these phenomena, scientists gain a deeper understanding of our planet's geology and can work towards better prediction and mitigation strategies. While volcanic eruptions can be devastating, they also remind us of the Earth's awe-inspiring power and its ability to shape and transform landscapes. By respecting and learning from these natural wonders, we can develop strategies to coexist with volcanic activity and protect vulnerable communities. Volcanic hazards and safety measures. Volcanic eruptions are among the most powerful and visually captivating natural phenomena on Earth. However, they also pose significant hazards to human life, property, and the environment. Understanding these hazards and implementing appropriate safety measures is crucial for communities living in close proximity to active volcanoes. Pyroclastic flows are among the most dangerous volcanic hazards. These fast-moving currents of superheated gas, ash, and volcanic debris can travel at incredible speeds, often reaching temperatures of several hundred degrees Celsius. Pyroclastic flows can devastate everything in their path, incinerating forests, buildings, and causing significant loss of life. The suddenness and unpredictability of these flows make them particularly challenging to escape. Safety measures. Maintain awareness of volcanic activity through official monitoring agencies and local authorities. Develop and practice evacuation plans that outline safe routes and designated meeting points. Identify and designate secure shelters away from potential pyroclastic flow paths. Educate the community about the dangers of pyroclastic flows and the importance of immediate evacuation. Volcanic eruptions release enormous quantities of fine ash and larger rock fragments called tephra into the atmosphere. These particles can be carried by wind for hundreds of kilometers, blanketing large areas with ash. Volcanic ash can cause respiratory problems, damage infrastructure, disrupt transportation systems, contaminate water supplies, and pose risks to agriculture, livestock, and human health. Use appropriate respiratory masks or coverings to prevent inhalation of fine ash particles. If evacuation is not possible, stay indoors and seal windows, doors, and ventilation systems to minimize ash entry. Wear long-sleeved shirts, long pants, and goggles to shield the skin and eyes from abrasive ash particles. Develop guidelines for safe ash removal and disposal to minimize health and environmental impacts. Lahars are mudflows composed of volcanic debris mixed with water, often triggered by heavy rainfall, rapid snowmelt, or the collapse of a volcanic crater lake. These fast-moving slurries of mud, boulders, and debris can travel down valleys, river channels, and canyons at high speeds, causing extensive damage to infrastructure and posing grave risks to communities downstream. Establish monitoring networks to detect lahars and issue timely warnings to vulnerable areas. Identify high-risk zones prone to lahars and develop evacuation routes and safe assembly points. Restrict human settlements and critical infrastructure in lahar-prone areas to minimize exposure. Construct dams, retention ponds, or channels to divert and contain lahars, reducing downstream impacts. Volcanic hazards pose significant risks to human lives, infrastructure, and the environment. With proper understanding, preparedness, and implementation of safety measures, communities can mitigate these risks and enhance their resilience to volcanic eruptions. Education and awareness play a crucial role in ensuring public safety. It is essential for individuals living in volcanic areas to stay informed about the status of volcanoes through reliable monitoring agencies and follow the instructions provided by local authorities. Developing and practicing evacuation plans, along with identifying safe shelters, can save lives during sudden volcanic events like pyroclastic flows. Dealing with volcanic ash requires adequate respiratory protection and the implementation of cleanup protocols to minimize health and environmental impacts. Additionally, recognizing the threat of lahars and establishing early warning systems can allow for timely evacuation and land use planning to minimize exposure to these destructive mudflows. Monitoring volcanic gas emissions and implementing evacuation protocols are key to protecting communities from the immediate health effects of gases and the formation of acid rain. By prioritizing public safety and incorporating scientific knowledge and technological advancements, we can effectively reduce the impact of volcanic hazards on society. Furthermore, interdisciplinary collaboration among scientists, emergency responders, government agencies, and local communities is vital for comprehensive volcano risk management. By pooling resources, sharing expertise, and conducting ongoing research, we can continuously improve our understanding of volcanic processes and enhance preparedness measures. While we cannot prevent volcanic eruptions, we can strive to minimize their impact by prioritizing safety, preparedness, and resilience. By respecting the power of nature and working together, we can navigate the challenges posed by volcanic hazards and ensure the well-being of communities living in proximity to these captivating yet dangerous natural wonders. Thanks for watching. We appreciate it. Please consider subscribing.